Back in 2017, humanity encountered our first confirmed interstellar visitor, a mysterious object called Oumuamua. Scientists at first thought they had a pretty good idea of what it was, but then came 2I-Borisov in 2019, and after that 3I-ATLAS in 2025. Each new discovery has made Oumuamua look more and more bizarre, and honestly, even potentially artificial. As we study more of these interstellar objects, the strange properties of our first visitor really stand out like a cosmic anomaly. So today we're diving into how recent discoveries are making Oumuamua seem less like a natural space rock, and more like, well, something entirely different. The discovery of 3I-ATLAS. The astronomical world was really shaken up when the Asteroid Terrestrial Impact Last Alert System, or ATLAS, detected humanity's third confirmed interstellar visitor in January 2025. Unlike its predecessors, 3I-ATLAS showed immediately recognizable comet-like behavior, with a distinct tail and visible outgassing as it got closer to the Sun. The object, measuring about 800 meters across, followed a classic hyperbolic trajectory, which made its extrasolar origin totally clear. There was just no doubt about it. What made this discovery especially significant was how normal it appeared compared to the enigmatic Oumuamua that had baffled scientists for years. 3I-ATLAS behaved exactly as astronomers would expect an interstellar comet to behave. It brightened in a predictable way as solar heating vaporized surface ices, creating the classic coma and tail that define cometary objects. The discovery team, led by astronomers at the University of Hawaii, immediately jumped into comparative studies with previous interstellar visitors. As data started pouring in from observatories all over the world, one thing really stood out. 3I-ATLAS was acting like a completely normal natural comet, which just made Oumuamua's bizarre properties seem even more anomalous and, yeah, potentially artificial. This stark contrast forced scientists to reconsider everything they thought they knew about our first interstellar guest. The Oumuamua discovery. On October 19, 2017, the Pan-STARRS 1 telescope in Hawaii detected a faint moving object that would, honestly, revolutionize our understanding of interstellar visitors. Initially designated 2017 U1, the object was quickly reclassified as the first confirmed interstellar asteroid and given the Hawaiian name Oumuamua, which means scout or messenger from afar. The discovery team, led by Dr. Robert Warwick at the University of Hawaii, realized they were seeing something truly unprecedented, an object with a hyperbolic orbit showing it had come from outside our solar system. Within just days of detection, observatories worldwide turned their instruments toward this cosmic visitor, racing against time as it rapidly moved away from the Sun. The object's discovery challenged existing classification systems, actually forcing the International Astronomical Union to create a whole new designation category for interstellar objects. Oumuamua's trajectory indicated it had been traveling through interstellar space for millions of years before its chance encounter with our solar system. The excitement was just palpable in the astronomical community. Humanity had finally found definitive proof that objects regularly travel between star systems, opening up a new window into the broader galactic environment and the materials that exist in the vast spaces between stars. Oumuamua's strange properties. Oumuamua immediately stood out as unlike any object previously observed in our solar system, displaying properties that really defied our conventional understanding of asteroids and comets. The object's light curve variations suggested an extremely elongated shape, possibly 10 times longer than it was wide, kind of like a cosmic cigar or needle, instead of the usual rounded shapes we see with asteroids. Its unusual geometry meant Oumuamua tumbled through space every 7.3 hours, causing dramatic brightness changes as different surfaces reflected sunlight toward Earth. Even more puzzling was its extraordinary speed. The object was traveling at 26 kilometers per second relative to the Sun, much faster than typical solar system objects. Spectroscopic observations showed a reddish surface similar to some asteroids, but Oumuamua had no signs of water vapor, dust, or gas emissions that we usually see with comets when they're heated by the Sun. This absence of outgassing was especially strange since most objects from the outer reaches of space contain volatile materials that should vaporize when they get close to our star. The combination of unusual shape, high speed, lack of cometary activity, and mysterious surface composition made Oumuamua a real cosmic puzzle, challenging some of our most fundamental assumptions about interstellar objects and what we expect them to be like. The acceleration mystery. The most perplexing aspect of Oumuamua really emerged when astronomers analyzing its trajectory discovered that the object was accelerating away from the sun in a way that just didn't match what we'd expect from gravitational forces alone. This unexpected acceleration, first reported by Dr. Marco Micheli from the European Space Agency, suggested that some force was actively pushing Oumuamua beyond the influence of solar gravity. Now, typically, comets show similar acceleration because of outgassing. When solar heating vaporizes surface materials, the expelled gas creates this kind of rocket-like thrust. But Oumuamua, well, it showed no visible signs of outgassing, no detectable coma, and absolutely no dust trail that could explain this mysterious acceleration. The acceleration itself was small but definitely measurable, about 2.5 times 10 to the -6th meters per second squared, which over time was enough to significantly alter the object's trajectory. This phenomenon kind of violated everything scientists understood about how inert space rocks should behave when only gravity is at play. The absence of observable outgassing while still experiencing this unexplained acceleration ended up creating a scientific paradox that, honestly, sparked some pretty intense debate within the astronomical community. Some researchers proposed exotic explanations like sublimating hydrogen ice or other invisible processes, while others started to consider more radical possibilities, including the controversial suggestion that Oumuamua might actually represent humanity's first encounter with artificial technology from another civilization. Scientific investigations. So, following Oumuamua's mysterious behavior, scientists all over the world launched comprehensive observational campaigns using the most powerful telescopes we have to try to understand this enigmatic visitor. The Spitzer Space Telescope, for example, conducted crucial infrared observations that provided insights into the object's thermal properties and surface composition. These observations revealed that Oumuamua had an unusually reflective surface with an albedo of about 0.1, which is similar to carbon-rich asteroids but, inconsistent with what we see in typical icy comets. The object's thermal signature also indicated it wasn't actively shedding material, confirming the absence of traditional cometary outgassing, even though it was so close to the sun. Radio telescope arrays, including the Green Bank telescope, carried out search for extraterrestrial intelligence protocols to see if there were any artificial signals coming from the object, but none were found. Meanwhile, ground-based observatories worldwide coordinated their observations to precisely track Oumuamua's trajectory and rotation, building detailed models of its shape and behavior. These collaborative efforts showed that the object's acceleration just couldn't be chalked up to measurement errors or any previously unknown gravitational influences. All this data painted a picture of an object that was, frankly, unlike anything in our solar system's inventory, exhibiting properties that really challenged our conventional understanding of natural space debris and raised some pretty profound questions about its true nature and origin. The alien hypothesis. Harvard astrophysicist Dr. Avi Loeb, he really shocked the scientific community by proposing that Oumuamua might actually be humanity's first encounter with artificial extraterrestrial technology. In his controversial analysis, Loeb suggested that the object could be an artificial light sail, a thin, reflective sheet designed to catch solar radiation for propulsion, kind of like concepts that human engineers have developed for interstellar travel. This hypothesis would elegantly explain Oumuamua's unusual acceleration without any visible outgassing, since radiation pressure from sunlight could provide the observed thrust on a surface that's sufficiently thin and reflective. Loeb calculated that a light sail only millimeters thick but hundreds of meters wide could, in fact, exhibit exactly the acceleration patterns observed in Oumuamua's trajectory. His proposal, which he published in the Astrophysical Journal Letters, argued that dismissing the artificial origin hypothesis without proper consideration was, honestly, just unscientific bias against extraordinary possibilities. The light sail theory generated intense controversy within the astronomical community, with many of Loeb's colleagues criticizing him for promoting what they considered sensationalist speculation without enough evidence. However, Loeb defended his analysis by pointing out that extraordinary claims require extraordinary investigation, and that ruling out artificial origins just because of our preconceptions about extraterrestrial technology would be scientifically irresponsible. His hypothesis sparked global media attention and really renewed public interest in the search for extraterrestrial intelligence. The dark comet theory. In response to Loeb's alien hypothesis, astronomers Dr. Darrell Seligman from the University of Chicago and Dr. Gregory Laughlin developed an alternative explanation they termed the dark comet theory. Their model proposed that Oumuamua was composed primarily of hydrogen ice, frozen molecular hydrogen that would be, well, nearly invisible when sublimating in space. Unlike water ice, which creates visible clouds and tails when heated, hydrogen gas would be virtually undetectable using conventional observational techniques. This invisible outgassing could explain Oumuamua's mysterious acceleration without contradicting the absence of visible cometary activity. The researchers calculated that an object made largely of hydrogen ice would exhibit exactly the thermal and dynamical properties observed in Oumuamua, including its unusual reflectivity and acceleration pattern. Their theory suggested that hydrogen icebergs might be common in interstellar space, formed in the extremely cold conditions between stars where molecular hydrogen can freeze into solid form. This natural explanation provided a way to understand Oumuamua's anomalous behavior without invoking artificial origins or revolutionary physics. The dark comet model gained support from several prominent astronomers who preferred conventional explanations over extraterrestrial technology hypotheses. However, the theory also faced criticism regarding the stability of hydrogen ice under the thermal conditions Oumuamua experienced during its solar system passage. The ongoing debate. Despite the dark comet theory's scientific appeal, Dr. Avi Loeb remained skeptical of natural explanations for Oumuamua's behavior, continuing to advocate for serious consideration of artificial origins. Loeb criticized the hydrogen ice hypothesis on several grounds, arguing that such objects would be extremely fragile and unlikely to survive intact during interstellar travel spanning millions of years. He pointed out that hydrogen ice sublimates at very low temperatures, making it unlikely that sufficient material could remain frozen during Oumuamua's approach to the Sun to explain the observed acceleration. Additionally, Loeb noted that the dark comet theory required specific and somewhat contrived conditions to work, while the light sail hypothesis provided a more straightforward explanation for all observed anomalies. The scientific community remained deeply divided, with most astronomers favoring natural explanations while acknowledging the limitations of current models. The debate highlighted fundamental questions about scientific methodology, how much evidence is required to consider extraordinary hypotheses, and whether the search for conventional explanations sometimes prevents serious consideration of revolutionary possibilities. Leading journals published papers on both sides of the argument, with each camp identifying weaknesses in opposing theories. This ongoing controversy demonstrated how a single mysterious object could expose deep philosophical divisions within the scientific community about the nature of evidence, the burden of proof, and the appropriate response to phenomena that challenge established understanding. Project Lyra mission concept. The mystery surrounding Oumuamua inspired ambitious mission concepts designed to intercept and study the object directly before it disappeared forever into interstellar space. Project Lyra, proposed by researchers at the European Space Agency and Johns Hopkins Applied Physics Laboratory, outlined a technically feasible spacecraft mission that could potentially catch up with Oumuamua using advanced propulsion systems and gravity-assist maneuvers. The mission concept involved launching a high-speed probe that would use multiple planetary gravity assists, including flybys of Earth and Jupiter, to achieve the tremendous velocity needed to intercept an object already traveling at interstellar speeds. Advanced ion propulsion systems would provide additional acceleration, potentially allowing the spacecraft to reach Oumuamua within 15 to 20 years of launch. The probe would carry sophisticated instruments including high-resolution cameras, spectrometers, and sample collection systems designed to definitively determine the object's composition, internal structure, and origin. Mission planners calculated that direct observation and analysis could resolve the debate between natural and artificial hypotheses once and for all. However, the enormous technical challenges and costs associated with such an ambitious interstellar chase mission made immediate implementation unlikely. The Project Lyra concept demonstrated both human ingenuity in mission design and the frustrating reality that our current technology limits our ability to investigate the most intriguing cosmic phenomena that briefly visit our solar system. The Future Hunt. The upcoming Vera C. Rubin Observatory, scheduled to begin operations in 2025, promises to revolutionize our ability to detect and study interstellar visitors like Oumuamua. This powerful survey telescope will scan the entire visible sky every few nights, potentially discovering dozens of interstellar objects annually, and providing the statistical sample needed to understand whether Oumuamua represents a typical example or a genuine anomaly. Early detection by Rubin Observatory would allow astronomers months or years to study new interstellar visitors, rather than the brief weeks available for Oumuamua analysis. The comparison between natural objects like 3I-ATLAS and the enigmatic properties of Oumuamua will become increasingly important as more interstellar visitors are cataloged and characterized. If future discoveries consistently show normal cometary behavior while Oumuamua remains unique in its anomalous properties, the case for artificial origins would strengthen significantly. Conversely, finding additional objects with similar mysterious characteristics would suggest previously unknown natural processes operating in interstellar space. The resolution of Oumuamua's mystery may ultimately depend on discovering whether it represents an isolated cosmic oddity or the first member of a new class of interstellar objects. As our observational capabilities improve, and our sample of interstellar visitors grows, we may finally answer one of the most profound questions in modern astronomy. Did humanity's first confirmed interstellar guest represent our first encounter with alien technology? So there you have it. As we discover more normal interstellar objects like 3I/ATLAS, Oumuamua's bizarre properties become increasingly difficult to explain through natural processes alone, whether it's an alien light sail, a hydrogen iceberg, or something entirely different remains one of astronomy's greatest mysteries. What do you think Oumuamua really was? Share your thoughts in the comments. If you enjoyed this cosmic mystery, like and share this video, and subscribe to Sci and Y for more incredible space discoveries. Until next time, keep looking up. On September 26, 2022, NASA achieved something truly unprecedented. They deliberately crashed a spacecraft into an asteroid at 6.6 kilometers per second and, get this, completely changed its orbit. The DART mission wasn't just about proving we could hit a space rock. No, it was humanity's first successful test of planetary defense technology. But what happened after the collision honestly shocked scientists and revealed truths about asteroids that nobody really expected. The aftermath of this cosmic collision is rewriting everything we thought we knew about protecting Earth from space threats. The journey to impact. NASA's Double Asteroid Redirection Test, or DART, began its historic journey on November 24, 2021, launching from Cape Canaveral Space Launch Complex 40 atop a SpaceX Falcon 9 rocket. The refrigerator-sized spacecraft traveled for nearly 10 months across 11 million kilometers of space to reach its target, a small asteroid moonlet called Dimorphos. The mission team, led by project scientist Dr. Nancy Chabot at the Johns Hopkins Applied Physics Laboratory, had meticulously planned every detail of this unprecedented experiment. Unlike previous space missions that aimed to study celestial objects, DART was designed with one purpose: to slam into Dimorphos and change its orbital path around the larger asteroid Didymos. The spacecraft carried advanced navigation systems that would allow it to autonomously guide itself to impact during the final 4 hours of flight, since the 11-minute communication delay with Earth made real-time control totally impossible. As DART approached its target, onboard cameras captured dramatic images of the asteroid growing larger and larger, marking humanity's first intentional collision with another world for planetary defense purposes. The perfect target. Dimorphos proved to be the ideal testing ground for this groundbreaking experiment, measuring approximately 160 meters in diameter and orbiting its larger companion Didymos every 11.9 hours. The binary asteroid system, located about 11 million kilometers from Earth at the time of impact, posed no threat to our planet, making it a safe target for this high-stakes test. Didymos, the larger asteroid measuring 780 meters across, served as the gravitational anchor for its smaller moonlet. Scientists chose this system because any change in Dimorphos's orbit could be precisely measured from Earth, using ground-based telescopes and radar systems. The asteroid pair was discovered in 1996, and had been extensively studied, providing researchers with detailed baseline measurements of their orbital characteristics. The proximity of the two asteroids meant that even a small change in Dimorphos's velocity would produce a measurable shift in its orbital period around Didymos. This binary system represented the perfect natural laboratory for testing kinetic impactor technology, close enough to Earth for accurate observation, large enough to produce detectable changes, yet far enough away to ensure complete safety for our planet throughout the experiment. The moment of impact. At exactly 23:14 UTC on September 26, 2022, DART slammed into Dimorphos at a closing speed of 6.14 kilometers per second, releasing kinetic energy equivalent to approximately 2.5 tons of TNT. The collision occurred with pinpoint accuracy, striking the asteroid's surface and instantly vaporizing the 610-kilogram spacecraft along with a portion of the asteroid's rocky material. Ground-based telescopes around the world captured the dramatic moment as a brilliant flash of light erupted from the impact site, followed by an expanding cloud of debris that grew brighter over several hours. The Hubble Space Telescope and James Webb Space Telescope immediately began observing the aftermath, documenting the evolution of the ejecta plume as it stretched across thousands of kilometers of space. Within minutes of impact, the debris cloud had expanded beyond Dimorphos itself, creating a spectacular tail of material that resembled a comet's tail stretching behind the asteroid. Amateur astronomers joined professional observatories in tracking the collision's effects, witnessing history as humanity demonstrated its ability to alter the path of a celestial object. The impact created seismic waves that rippled across Dimorphos' surface, potentially reshaping the asteroid's internal structure in ways that scientists are still working to understand. Beyond all expectations. The results of the DART impact exceeded every prediction and shattered the mission's success criteria. Instead of the minimum 73-second change in orbital period that would have declared the test successful, Dimorphos' orbit around Didymos shortened by an astounding 32 minutes. This dramatic change represented a 26-fold improvement over the mission's baseline requirements, proving that kinetic impactor technology was far more effective than scientists had dared to hope. The massive orbital change resulted not just from the direct momentum transfer of the spacecraft's impact, but from the unexpected efficiency of the momentum multiplication effect created by the ejected debris. As material blasted away from the impact site, it carried additional momentum in the opposite direction, acting like a natural rocket engine that amplified the deflection effect. Dr. Tom Statler, DART program scientist at NASA, described the results as a watershed moment for planetary defense and humanity's ability to influence our cosmic environment. The orbital change was so significant that it could be measured by small telescopes and even confirmed by radar observations from Arecibo Observatory and the Goldstone Deep Space Communications Complex. This level of deflection meant that if Dimorphos had been on a collision course with Earth, the impact would have shifted its trajectory by hundreds of thousands of kilometers. The mysterious ejecta cloud. The debris cloud created by DART's impact revealed secrets about asteroid composition that puzzled scientists worldwide. Instead of the uniform dust plume that computer models predicted, the ejecta displayed complex structures including multiple debris streams, spiral patterns, and irregular particle distributions that suggested Dimorphos had a far more complex internal structure than anticipated. Dr. Christina Thomas at Northern Arizona University, who led the observational campaign, noted that the debris cloud evolved in unexpected ways over the following weeks. Some particles were ejected at speeds exceeding 500 meters per second, while others moved much more slowly, creating distinct populations of material with different trajectories and behaviors. The cloud's asymmetric shape indicated that Dimorphos wasn't a solid uniform rock, but likely a rubble pile, a loose collection of smaller rocks and boulders held together by weak gravitational forces. High-resolution images from ground-based telescopes revealed that the ejecta contained both fine dust particles and larger chunks of material, some potentially meters in size. The debris cloud's brightness variations suggested that different types of material were being ejected from various depths within the asteroid, providing unprecedented insights into the internal layering and composition of small solar system bodies. Hera's investigative mission. Recognizing the need to understand DART's impact in detail, the European Space Agency launched the Hera mission in October 2024 to conduct a comprehensive post-impact investigation. This follow-up mission represents an unprecedented example of international cooperation in planetary defense, with Hera scheduled to arrive at the Didymos system in late 2026 to examine the crater left by DART's collision. The spacecraft carries advanced instruments including high-resolution cameras, thermal imagers, and radar subsystems designed to map both asteroids down to centimeter-scale resolution. Hera will measure the precise size and depth of DART's impact crater, analyze the composition of exposed subsurface material, and determine how the impact altered the internal structure of both Dimorphos and its parent asteroid Didymos. The mission will also deploy two small CubeSats called Juventus and Milani to conduct complementary investigations, including the first radar sounding of an asteroid's interior and detailed gravitational field mapping. Dr. Patrick Michel, Hera's principal investigator, emphasized that understanding the physical properties revealed by DART's impact is crucial for designing future deflection missions. The data collected by Hera will validate computer models used to predict deflection effectiveness, and provide the foundation for operational planetary defense systems. Unraveling asteroid mysteries. The DART impact revealed that small asteroids like Dimorphos are far more complex than scientists previously understood, fundamentally changing how we think about these cosmic building blocks. Pre-impact models assumed asteroids were relatively simple objects with predictable responses to external forces, but the dramatic success of the deflection demonstrated that rubble pile asteroids behave more like fluid structures than solid rocks. Dr. Andy Rivkin at the Johns Hopkins Applied Physics Laboratory noted that the impact's efficiency suggested Dimorphos has very low internal cohesion, allowing the impact energy to propagate throughout the entire structure and eject material from multiple locations. The asteroid's surface appears to be covered in loose regolith, fine, rocky debris accumulated over millions of years, that was easily disturbed by the impact's shock waves. Spectroscopic observations of the ejecta revealed that Dimorphos contains ordinary chondrite minerals, similar to the most common meteorites found on Earth, but with unusual proportions that suggest a complex formation history. The impact also provided insights into how small asteroids respond to tidal forces from their parent bodies, with evidence suggesting that Dimorphos experiences ongoing surface changes due to its proximity to Didymos. These discoveries have profound implications for understanding asteroid evolution, the formation of binary systems, and the potential resources available on near-Earth asteroids for future space missions. Complications for future defense. While DART proved that kinetic impactors can deflect asteroids, the mission also revealed complications that will influence future planetary defense strategies. The unexpectedly large orbital change, while impressive, highlighted just how difficult it is to predict exactly how different asteroids will respond to impact. Dr. Nancy Chabot emphasized that the momentum multiplication factor, the ratio of total momentum change to the spacecraft's initial momentum, varied significantly from pre-impact predictions, reaching values between 2.2 and 4.9 depending on the measurement method. This variability means that future deflection missions will require detailed advanced characterization of target asteroids to predict their response accurately. The complex ejecta pattern suggested that asteroid internal structure, surface composition, and rotation state all influence deflection efficiency in ways that current models just don't fully capture. The discovery that small asteroids behave more like loosely bound rubble piles than solid objects means that deflection strategies must account for potentially dramatic differences in material properties between different asteroid types. Mission planners now recognize that successful planetary defense will require a library of deflection techniques tailored to specific asteroid characteristics, rather than a one-size-fits-all approach. The DART results also emphasize the importance of early detection and characterization, since deflection effectiveness depends critically on understanding an asteroid's physical properties years before any potential impact threat. Global Planetary Defense Initiative. The success of the DART mission has catalyzed unprecedented international cooperation in planetary defense, transforming what was once considered science fiction into practical space policy. NASA's Planetary Defense Coordination Office, established in 2016, now works closely with the European Space Agency, Japan's JAXA, and other international partners to develop comprehensive strategies for detecting and deflecting hazardous near-Earth objects. The United Nations Office for Outer Space Affairs has established new protocols for sharing asteroid tracking data and coordinating deflection missions, recognizing that planetary defense is a global responsibility requiring multinational collaboration. Ground-based survey telescopes like the Catalina Sky Survey in Arizona and the Linear program in New Mexico continue discovering new potentially hazardous asteroids at rates exceeding 1,000 per year, building a comprehensive catalog of objects that might someday threaten Earth. Space-based detection systems, including NASA's NEOWISE mission and the planned NEO Surveyor telescope, will dramatically improve our ability to find and track smaller asteroids that ground-based systems might miss. The establishment of the International Asteroid Warning Network ensures that discovery data reaches decision-makers quickly enough to enable deflection missions if needed. These coordinated efforts represent humanity's first serious attempt to protect our planet from cosmic threats that have caused mass extinctions throughout Earth's history. The future of planetary defense. The DART mission's spectacular success has laid the foundation for humanity's first operational planetary defense system, but it also revealed how much we still need to learn about deflecting dangerous asteroids. Future missions will build on DART's legacy by testing different deflection techniques including gravity tractors, nuclear standoff detonations, and enhanced kinetic impactors designed for specific asteroid types and threat scenarios. NASA's follow-up missions are already in development, including concepts for multi-spacecraft deflection systems that could handle larger asteroids or provide backup capabilities for critical deflection attempts. The double asteroid redirection test proved that humanity possesses the technological capability to alter the course of celestial objects, marking our species' transition from passive observers of cosmic events to active participants in shaping our solar system's dynamics. Advanced computer simulations now incorporate DART's impact data to model deflection scenarios with unprecedented accuracy, enabling mission planners to design precise interventions for specific threat asteroids. The mission's success has also sparked development of rapid response deflection technologies that could be deployed on shorter timescales for newly discovered threats. Most importantly, DART demonstrated that international cooperation and scientific expertise can overcome seemingly impossible challenges, providing a template for tackling other global threats that require coordinated human action on planetary scales. So there you have it. NASA didn't just hit an asteroid, they revolutionized planetary defense and revealed that asteroids are far stranger than we imagined. Which discovery about the DART mission surprised you the most? Let me know in the comments below. If you enjoyed learning about humanity's first successful planetary defense test, make sure to like this video, share it with someone who loves real space breakthroughs, and don't forget to subscribe to Sci&Y for more incredible discoveries about our universe. Until next time, keep exploring the cosmos. The Juno spacecraft has been revolutionizing our understanding of Jupiter since its arrival in 2016. Its deep scans beneath the clouds have revealed mysteries that challenge everything we thought we knew about the gas giant. Beneath Jupiter's swirling atmosphere lies not just storms, but an enigmatic heart pulsing with powerful forces unlike anything seen before. From terrifying cyclones spinning backwards to a fuzzy core that defies physics, Juno's discoveries are rewriting textbooks. Today we're diving into the most shocking revelations about the largest planet in our solar system. The mysterious central storm discovery. Juno's ultraviolet and microwave instruments uncovered something absolutely terrifying at Jupiter's core, a massive cyclonic storm that shouldn't exist according to our understanding of planetary physics. Unlike the surface storms we can observe from Earth, this central storm spins in the opposite direction to Jupiter's rotation and measures approximately 10,000 kilometers wide, making it larger than Earth itself. In 2017, scientists led by Dr. Scott Bolton from the Southwest Research Institute first reported this bizarre storm that completely defied existing models of Jovian weather patterns and atmospheric dynamics. The storm's presence suggests Jupiter's interior is far more violent and chaotic than anyone previously believed, with turbulent motions that create powerful electromagnetic effects and possibly influence the planet's extraordinary auroras. This discovery opened terrifying new questions about how gas giants maintain their internal heat sources and complex weather systems, forcing scientists to completely rethink everything they thought they knew about planetary atmospheres. The central storm's backwards rotation indicates incredibly complex internal dynamics that researchers are still desperately trying to understand, representing one of the most significant and disturbing findings from Juno's exploration of Jupiter's mysterious depths. The beginning of the mission. Launched on August 5, 2011, the Juno spacecraft embarked on a nearly 5-year journey through the hostile depths of space to reach Jupiter, finally arriving on July 4, 2016. The spacecraft's primary mission was to understand Jupiter's formation, atmospheric composition, massive magnetosphere, and complex gravity field through unprecedented close-range observations. Equipped with sophisticated instruments including the microwave radiometer and Jovian infrared auroral mapper, Juno follows a highly elliptical orbit around Jupiter every 53 days, diving dangerously close through the planet's radiation-filled cloud tops. Mission Commander Scott Bolton and NASA engineering teams spent years developing meticulous protection systems to shield Juno from Jupiter's deadly radiation belts, designing a specialized titanium radiation vault to protect the spacecraft's sensitive electronics from being fried by the intense electromagnetic environment. This groundbreaking mission continues to push the absolute limits of planetary science and space exploration technology, offering humanity's best and closest look yet at the gas giant's mysterious core and incredibly complex magnetic environment. The spacecraft's highly elliptical orbit allows it to approach within just 4,200 kilometers of Jupiter's cloud tops during each perijove pass, collecting detailed measurements and data that were previously completely impossible to obtain. Jupiter is the world of chaos. Jupiter represents the ultimate manifestation of atmospheric chaos in our solar system, with weather patterns so violent and unpredictable, they make Earth's most severe storms look like gentle breezes. The planet's massive atmosphere consists primarily of hydrogen and helium gases, generating vertical wind speeds that regularly exceed 540 kilometers per hour, fast enough to tear apart any spacecraft attempting to enter its atmosphere. Jupiter's cloud layers reveal constantly shifting bands of storms, massive vortexes and lightning strikes that are thousands of times more powerful than anything experienced on Earth. These storm systems create extraordinary geometric patterns and vivid colors visible even through telescopes millions of kilometers away, painting Jupiter's surface in bands of orange, brown, and white. Juno's advanced observations confirmed the presence of massive lightning storms detected by its Jovian energetic particle detector instrument, which identifies highly energetic particles directly linked to these violent and unpredictable weather systems. This incredible atmospheric complexity makes Jupiter not merely a gas giant, but a living laboratory for studying extreme atmospheric dynamics and fundamental physics of fluid turbulence, operating at scales completely impossible to replicate on Earth. The planet's differential rotation means different latitudes rotate at dramatically different speeds, creating powerful shear forces that generate Jupiter's distinctive banded appearance. Io, the volcanic moon. Among Jupiter's 79 confirmed moons, Io stands out as the most volcanically active and geologically violent body anywhere in our solar system, making it a hellish world of constant eruptions and molten chaos. Its scarred surface is covered with hundreds of active volcanoes that continuously spew sulfur compounds and molten lava fountains reaching incredible heights of up to 500 kilometers above the surface. This relentless volcanic fury results from intense tidal heating caused by Jupiter's massive gravitational pull, combined with complex orbital resonances with neighboring moons Europa and Ganymede, creating internal friction that keeps Io's interior molten. Juno's detailed flybys and precise measurements combined with archival data from previous missions like Galileo help scientists understand Io's extreme geological processes and its crucial role in feeding charged particles into Jupiter's deadly magnetosphere. Io's plasma torus, a massive ring of highly ionized gases orbiting around Jupiter, directly influences the planet's radiation environment and provides essential insights into the complex interactions between Jupiter and its satellite system. The moon's sulfur-rich volcanic activity creates a unique and hostile environment, where surface temperatures vary dramatically from extremely cold regions in permanent shadow to areas heated to over 1,800 degrees Celsius by continuous volcanic activity, making Io one of the most geologically dynamic and dangerous worlds. Research on Jupiter's magnetic field. Juno's sophisticated magnetometer instruments have been absolutely crucial in mapping Jupiter's unprecedented magnetic field, which represents the strongest planetary magnetic field in our entire solar system, measuring approximately 14 times more powerful than Earth's protective magnetic shield. This immense magnetic field extends millions of kilometers into space, creating Jupiter's vast magnetosphere that completely dwarfs even the Sun's magnetic influence in the immediate vicinity of the giant planet. Leading scientists, including Dr. Heidi Becker from NASA's Jet Propulsion Laboratory, discovered completely unexpected asymmetries and highly localized regions of intense magnetism during Juno's dangerously close orbital passes through Jupiter's radiation belts. These groundbreaking findings strongly suggest incredibly complex dynamo action occurring deep beneath Jupiter's cloud layers, generated by powerful currents of flowing metallic hydrogen existing under extreme pressure in the planet's mysterious interior regions. Understanding this magnetic environment represents far more than just studying Jupiter. It provides essential insights into planetary magnetic field generation and the protective roles these fields play around worlds throughout the universe. The magnetic field's highly irregular and unpredictable structure clearly indicates that Jupiter's internal dynamics operate through mechanisms far more complex and violent than scientists previously imagined, with profound implications for understanding how massive planets generate and maintain their protective magnetic environments. Juno mission peaks under Jupiter's surface. Juno's precision gravity science investigation revealed one of the most shocking discoveries in planetary science. Jupiter's core is not the compact, solid metallic ball that scientists expected, but instead appears to be a fuzzy, diluted structure extending up to 50% of the planet's total radius. This absolutely astonishing discovery completely challenged and overturned previous models of gas giant planet formation that had been accepted by the scientific community for decades. Detailed gravitational data from the spacecraft indicates that heavy metallic elements are far more spread out throughout Jupiter's interior than anyone predicted, mixing extensively with lighter hydrogen and helium gases in a diffuse, semi-solid core structure. The international research team, led by Dr. Luciano Ies from Sapienza University of Rome, used incredibly precise spacecraft tracking techniques to measure subtle variations in Jupiter's complex gravity field, revealing these hidden internal structures that were completely invisible from external observations. These revolutionary results strongly suggest that Jupiter experienced an extremely violent and chaotic formation history involving massive planetary collisions or prolonged turbulent accretion periods during the early solar system's development. Unveiling this incredible complexity hidden beneath Jupiter's deceptively calm-looking cloud layers provides invaluable scientific clues about gas giant origins, evolution, and the fundamental processes that shape planetary formation throughout the universe, suggesting that giant planets form through far more chaotic and violent processes than previously understood. Jupiter's formation and composition. Jupiter formed approximately 4.5 billion years ago during the earliest phases of our solar system's chaotic development, primarily accumulating vast quantities of hydrogen and helium gases captured directly from the swirling protoplanetary disk surrounding the young sun. Its absolutely massive size, containing over 320 times Earth's total mass, provided sufficient gravitational power to retain these extremely light gases that smaller rocky planets like Earth and Mars could never hope to capture or hold. Juno's advanced spectral observation instruments confirm the presence of trace amounts of water vapor, ammonia, and methane compounds, distributed at varying depths throughout Jupiter's complex atmospheric layers, creating a chemical fingerprint of the planet's formation history. The presence and distribution of these molecular compounds helps scientists reconstruct the primordial materials that Jupiter accumulated during its formation, and provides crucial data about the radial mixing and chemical evolution of compounds over billions of years. Leading research by planetary atmospheric scientist Dr. Lee Fletcher from the University of Leicester enhances sophisticated computer models of Jupiter's atmospheric composition, revealing complex chemical gradients that indicate dynamic upwelling processes and vertical mixing of gases from deep interior regions. Understanding Jupiter's formation process and chemical evolution significantly improves scientific theories about planetary system development and helps predict the potential characteristics and formation mechanisms of gas giant exoplanets orbiting distant stars throughout our galaxy. Jupiter as Earth's protector. Jupiter functions as a massive celestial guardian for Earth and the inner solar system, using its immense gravitational influence to deflect or capture dangerous incoming comets and asteroids that could potentially cause catastrophic impacts on our planet. The planet's enormous magnetosphere and powerful gravitational field significantly reduce the impact rate of potentially hazardous objects in the inner solar system, possibly providing crucial protection that has allowed complex life to evolve and thrive on Earth over billions of years. However, Jupiter's protective role represents a complex double-edged sword. While its gravity shields us from many threats, it can also gravitationally perturb objects and send them on altered trajectories that intersect with Earth's orbital path around the Sun. Comprehensive studies by leading astronomers including Dr. Alan Stern from the Southwest Research Institute emphasize this complicated dual role, examining how Jupiter simultaneously facilitates both planetary protection and potentially dangerous dynamical chaos within our solar system's architecture. Understanding this delicate gravitational balance proves essential for accurately assessing the long-term evolution of Earth's environment and evaluating the likelihood of maintaining stable, life-supporting conditions necessary for biological evolution on planets and other star systems. Jupiter's gravitational influence has fundamentally shaped the orbital architecture of our entire solar system over billions of years, creating complex resonance patterns that affect asteroid and comet trajectories, ultimately influencing the delivery of water and organic materials to inner planets during their formation. The Great Red Spot Mystery. The Great Red Spot represents one of the most iconic and mysterious features in our solar system, a colossal storm system larger than Earth that has been continuously raging for several centuries, yet recently has been mysteriously shrinking at an alarming rate. First definitively observed and documented by astronomers in the 17th century, this massive anticyclonic storm currently spans approximately 16,000 kilometers across and rotates counterclockwise at terrifying speeds exceeding 432 kilometers per hour, creating winds powerful enough to destroy any human-made structure. Juno's sophisticated scientific instruments detected incredibly complex multi-layered cloud structures and intense lightning activity deep within the storm system, providing revolutionary new insights into the energy sources and physical mechanisms that have maintained this enormous weather phenomenon for hundreds of years. Leading researchers, including Dr. Heidi Becker from NASA's Jet Propulsion Laboratory, actively study the complex atmospheric dynamics driving the Great Red Spots concerning shrinkage and investigate potential changes in Jupiter's atmospheric composition, or internal energy flow patterns. The storm exemplifies the most powerful and persistent meteorological phenomena known to science, challenging our fundamental understanding of fluid mechanics and atmospheric physics operating on truly planetary scales. Recent detailed observations suggest the Great Red Spot may be gradually losing both its distinctive reddish coloration and its well-defined structural boundaries, raising serious scientific questions about whether this iconic feature will eventually disappear entirely, fundamentally altering Jupiter's appearance forever. Jupiter's rings and lesser moons. Jupiter possesses a surprisingly complex but faint ring system that was first discovered in 1979 by the Voyager 1 spacecraft during its historic flyby, revealing a delicate structure composed primarily of microscopic, dust-sized particles continuously supplied by meteoroid impacts on the planet's small inner moons. These rings, while dramatically less spectacular than Saturn's magnificent and well-known ring system, remain incredibly thin and faint, but play a surprisingly important role in Jupiter's complex magnetospheric environment and particle dynamics. Juno's detailed observations, combined with data from earlier exploratory missions, have identified 4 distinct main ring components and dozens of small, irregularly shaped moons existing within Jupiter's intense radiation-filled magnetosphere. Among these lesser-known moons, Amalthea and Thebes serve as primary dust contributors to the ring system through continuous bombardment by high-velocity micrometeorites that blast material from their surfaces into space. Understanding these smaller celestial bodies and their dynamic ring interactions offers valuable scientific clues about Jupiter's long-term evolution and the fundamental physical processes that shape planetary ring systems throughout our solar system and beyond. The ring particles undergo continuous replenishment cycles through ongoing impacts on the small moons, creating a dynamic equilibrium system where material is constantly being added through collisions while simultaneously being lost through various gravitational and electromagnetic processes, providing crucial insights into the complex gravitational interactions governing ring systems around giant planets. That's the incredible story of Juno's journey deep beneath Jupiter's clouds, uncovering mysteries that force us to completely rethink our understanding of the giant planet. What surprised you the most about these terrifying discoveries? Let us know in the comments below. If you enjoyed diving into Jupiter's darkest secrets like this video, share it with fellow space enthusiasts, and don't forget to subscribe to Sci&Y for more amazing space exploration stories. Until next time, keep looking up. A mysterious object from deep space is racing through our solar system at incredible speeds, and scientists are calling it the most significant interstellar discovery since Oumuamua. This visitor, officially designated 3I-ATLAS, is challenging everything we thought we knew about objects from other star systems. Moving at over 150,000 miles per hour and potentially stretching 12 miles across, it's massive compared to previous interstellar visitors. Today, we're diving into this groundbreaking discovery and exploring whether this cosmic stranger might be something far more extraordinary than a simple space rock. A rare visitor from deep space. The astronomy world was electrified when Dr. Larry Deneau and his team at the University of Hawaii detected humanity's third confirmed interstellar visitor racing through our solar system in late June 2025. Unlike the millions of asteroids and comets that call our solar system home, this object originated from the depths of interstellar space, carrying secrets from distant star systems billions of miles away. Statistical models developed by Dr. Alan Fitzsimmons at Queen's University Belfast suggest that only about one interstellar object per year enters our solar system within the detection range of current telescopes. Most pass through our cosmic neighborhood unnoticed, invisible to our instruments due to their small size and tremendous velocity through space. This latest visitor, however, stood out immediately due to its unusual characteristics and substantial size compared to previous discoveries. The rarity of these cosmic messengers means that each detection provides invaluable insights into the composition and evolution of distant planetary systems, offering glimpses into worlds we may never directly explore. Advanced computer simulations by planetary scientists indicate that millions of objects are ejected from star systems during planetary formation, creating a vast population of interstellar wanderers throughout our galaxy. The breaking discovery. The significance of discovering our third interstellar object represents a revolutionary moment in modern astronomical research, fundamentally changing how we understand the frequency and characteristics of these cosmic visitors. Dr. Robert Warwick, who originally discovered Oumuamua at the Pan-STARRS telescope, emphasized that each interstellar visitor provides unique windows into cosmic processes occurring around distant stars. These objects represent natural spacecraft that have traveled for millions of years through the harsh radiation environment of interstellar space before arriving in our solar system. The discovery of 3I-ATLAS marks a turning point in our understanding of how common these visitors actually are, with detection rates suggesting they may be far more numerous than previously estimated. Leading planetary scientist Dr. Michelle Bannister from the University of Canterbury notes that this object appears significantly larger than previous discoveries, potentially offering substantially more material to study and analyze with current telescope technology. The timing of this discovery coincides with revolutionary improvements in automated detection algorithms and machine learning techniques that can identify unusual moving objects among millions of stellar observations. This breakthrough represents the dawn of a new era in interstellar object research where systematic detection and comprehensive study of these cosmic wanderers will transition from extraordinary events to routine scientific observations within the next decade. The discovery story. The Asteroid Terrestrial Impact Last Alert System detected the first signs of this mysterious visitor during routine sky surveys designed to identify potentially hazardous objects approaching Earth. Dr. John Tonry from the University of Hawaii, who leads the ATLAS project, explained that the system's 4 telescope stations across Hawaii and South Africa scan the entire visible sky every few nights. The initial detection appeared as a faint moving point of light against the star-filled background, requiring sophisticated software algorithms to distinguish it from the countless asteroids and comets already cataloged in our solar system. Within 24 hours of the discovery, astronomers around the world began tracking the object's trajectory using the Minor Planet Center's Rapid Response Network. The confirmation process involved multiple observations from different telescopes to eliminate any possibility of measurement error or misidentification of this potentially historic discovery. Dr. Marco Micheli from the European Space Agency's NEO Coordination Center led the orbital analysis team that quickly realized the object's hyperbolic trajectory indicated an origin from outside our solar system. Once the interstellar nature was confirmed beyond doubt, the International Astronomical Union officially designated the object following established naming conventions for interstellar discoveries. The Discovery team immediately initiated a global observational campaign coordinated through the International Astronomical Union's telegram system to gather as much scientific data as possible. A stranger in our midst. So, 3I-ATLAS exhibits properties that set it apart dramatically from typical solar system objects, beginning with its extraordinary velocity measurements, indicating speeds over 40 kilometers per second relative to our Sun's reference frame. This hyperbolic excess velocity is characteristic of objects that have escaped the gravitational influence of other star systems and spent eons traveling through the vacuum of interstellar space. Preliminary photometric analysis by Dr. Daisuke Suzuki at the University of Tokyo suggests the object could measure up to 20 kilometers across, making it significantly larger than Oumuamua's estimated 400-meter length. The object's brightness variations indicate it may have an elongated or highly irregular shape with a rotation period of approximately 8.2 hours, similar to other interstellar visitors observed previously. Unlike most solar system comets, 3I-ATLAS shows minimal signs of outgassing or tail formation despite its approach toward the Sun, suggesting either a heavily processed surface or unusual bulk composition resistant to sublimation. Spectroscopic observations reveal a surface composition remarkably similar to carbonaceous chondrite meteorites, indicating the presence of organic compounds and water-bearing minerals. The combination of size, speed, and surface properties makes this visitor particularly intriguing for scientists seeking to understand the population and characteristics of objects wandering between star systems throughout our galaxy. The predecessors. The story of interstellar object discovery began with Oumuamua's detection on October 19, 2017, when Dr. Rob Warwick at the Pan-STARRS telescope in Hawaii identified humanity's first confirmed visitor from another star system. This cigar-shaped object measuring approximately 400 meters long exhibited puzzling non-gravitational acceleration that sparked intense debates about its composition and possible artificial origins among the scientific community. Oumuamua's discovery revolutionized our understanding of interstellar space, proving that objects regularly travel between star systems and occasionally pass through our cosmic neighborhood with measurable frequency. 2 years later, amateur astronomer Gennady Borisov discovered 2I-Borisov on August 30, 2019, our second confirmed interstellar visitor, which behaved much more like a typical comet with visible outgassing and a distinct coma and tail structure. These previous discoveries established the analytical framework for identifying and classifying interstellar objects, creating standardized detection protocols and analysis methods that proved invaluable for processing 3I-ATLAS data. Each interstellar visitor has contributed unique insights into the diversity of objects wandering through our galaxy, from the mysterious acceleration properties of Oumuamua to the more conventional cometary behavior exhibited by 2I-Borisov. The progression from these early discoveries to 3I-ATLAS demonstrates the rapid advancement in our technological capability to detect and comprehensively study these rare cosmic wanderers. The cosmic journey. 3I-ATLAS is following a precisely calculated hyperbolic trajectory that will carry it past several major solar system bodies before it exits our cosmic neighborhood forever. Dr. Davide Farnochia from NASA's Jet Propulsion Laboratory determined that the object will make relatively close approaches to both Mars and the Sun, providing unique opportunities for detailed observation and comprehensive scientific study. The trajectory analysis indicates the visitor entered our solar system from the galactic north direction, possibly passing near the orbit of Neptune, before being gravitationally focused toward the inner planets by Jupiter's massive influence. Current orbital models predict a closest approach to the Sun of approximately 1.1 astronomical units in early 2026, which will provide optimal conditions for thermal and spectroscopic analysis. Scientists are particularly interested in monitoring any changes in the object's rotational state and surface properties as it encounters different thermal environments during its solar approach. The gravitational influence of our solar system's planets will slightly alter the object's trajectory, increasing its velocity by approximately 2.3 kilometers per second relative to its entry conditions. After completing its journey through our solar system, 3I-ATLAS will continue traveling through interstellar space for millions more years, potentially encountering other star systems in the distant galactic future. This cosmic odyssey represents a journey spanning vast distances and enormous timescales, highlighting the dynamic nature of our galaxy where objects regularly migrate between stellar neighborhoods through gravitational interactions. A scientific gold mine. The discovery of 3I-ATLAS presents an unprecedented opportunity for scientists to study pristine material from another star system using the most advanced astronomical instruments ever developed. Dr. Stefano Bagnulo from Armagh Observatory and Planetarium is leading international polarimetry campaigns to analyze the object's surface texture and mineral composition in remarkable detail. The James Webb Space Telescope has allocated precious observing time to conduct infrared spectroscopy, potentially identifying specific chemical compounds and crystalline structures that formed around distant stars. Dr. Bin Yang from the European Southern Observatory is coordinating ground-based spectroscopic observations that have already detected water ice signatures and complex organic molecules on the object's surface. Scientists are particularly eager to understand how interstellar radiation and cosmic ray bombardment over millions of years have altered the object's surface chemistry during its journey through space. The thermal behavior of 3I-ATLAS as it approaches perihelion will provide critical insights into its internal structure, revealing whether it contains subsurface volatile reservoirs that could sublimate and create observable outgassing phenomena. These comprehensive observations contribute to our broader understanding of planetary formation processes around other stars, offering direct samples of materials and conditions that exist throughout our galaxy. The scientific value of this discovery extends far beyond simple academic curiosity, potentially informing future space exploration strategies and our ongoing search for habitable worlds around distant stellar systems. Unanswered questions. Despite intensive international observation efforts coordinated through major astronomical organizations, 3I-ATLAS remains shrouded in fundamental mysteries that challenge our understanding of interstellar objects. Dr. Matthew Knight from the University of Maryland emphasizes that the object's true bulk density remains uncertain, with estimates ranging from 0.5 to 2.5 grams per cubic centimeter, depending on different assumptions about its internal structure. Scientists are puzzled by the apparent lack of significant dust production, even as the object approaches the Sun, which raises questions about its surface composition and the content of subsurface volatiles. Dr. Quanzi Ye from the University of Maryland has identified some unusual photometric variations that could indicate an irregular shape, active surface processes, or maybe even the shadows of impact craters, though natural explanations are still considered more likely than artificial modifications. Researchers are struggling to determine whether 3I-ATLAS originated as a primordial comet, a collisional fragment, or a planetesimal ejected during planetary system formation in its parent star system billions of years ago. The object's rotational characteristics and internal mass distribution remain largely unknown, mostly due to the extreme distance and the limited observation time available before it moves beyond telescope range. Perhaps most intriguingly, scientists cannot definitively determine the object's formation environment or parent star system, though chemical analysis may eventually provide some clues about its stellar birthplace. These unanswered questions really highlight both the inherent limitations of remote sensing technology and the fundamental challenges of studying objects that spend only brief periods within range of our most powerful ground-based and space-based observatories. The alien question. The possibility that 3I-ATLAS could represent artificial technology from an extraterrestrial civilization remains a topic of legitimate scientific discussion, though the vast majority of researchers strongly favor natural explanations. Dr. Avi Loeb from Harvard University, who controversially proposed that Oumuamua might be an alien light sail, has expressed measured interest in 3I-ATLAS while emphasizing the importance of extraordinary evidence for extraordinary claims. The object's substantial size and unusual surface properties make it particularly intriguing for researchers investigating potential signs of extraterrestrial intelligence, though natural astrophysical processes can produce equally mysterious and counterintuitive phenomena. Dr. Seth Shostak from the SETI Institute emphasizes that interstellar objects naturally exhibit unusual characteristics due to their exotic origins and exposure to harsh interstellar radiation environments over geological timescales. The scientific community generally maintains that claims about alien technology require reproducible observational evidence and peer-reviewed analysis that eliminates all plausible natural explanations for observed phenomena. However, systematic study of these objects remains scientifically important for astrobiology research, since genuine artificial constructs would likely exhibit detectable engineering signatures distinct from natural geological and chemical processes. The ongoing debate surrounding potential artificial origins highlights the critical importance of maintaining open minds while applying rigorous scientific methodology to extraordinary discoveries that challenge conventional understanding. Regardless of its ultimate classification, 3I-ATLAS serves as an invaluable case study for developing standardized protocols to distinguish between natural phenomena and potentially artificial interstellar objects in future discoveries. Observing the visitor. Astronomical observatories worldwide have coordinated an unprecedented international campaign, utilizing every available technological resource to comprehensively study 3I-ATLAS before it moves beyond detection range. Dr. Casey Lissy from the Johns Hopkins Applied Physics Laboratory is leading James Webb Space Telescope observations that have already detected methane ice and complex hydrocarbon compounds on the object's surface. Ground-based observatories, including the Very Large Telescope in Chile and the Keck Observatory in Hawaii, are conducting detailed spectroscopic analysis using adaptive optic systems to identify specific chemical signatures and surface minerals. Dr. Tony Farnham from the University of Maryland is coordinating Hubble Space Telescope observations that contribute high-resolution imaging and ultraviolet spectroscopy, which are impossible from Earth's surface due to atmospheric interference. Radio telescopes, including the Green Bank Telescope, have conducted 150 hours of observations, monitoring the object for any artificial signals or unusual electromagnetic emissions, though none have been detected above background noise levels. The coordinated effort represents one of the most comprehensive and technologically advanced studies ever conducted on an interstellar visitor, utilizing cutting-edge instruments that were completely unavailable during Oumuamua's brief passage. Amateur astronomers around the world are also contributing valuable photometric observations using sophisticated CCD cameras and digital processing techniques that actually rival professional capabilities from previous decades. This global collaboration really exemplifies the international spirit of scientific discovery and demonstrates how mysterious cosmic phenomena can unite researchers across national and institutional boundaries in pursuit of fundamental knowledge about our universe and our place within the broader galactic community. 3I-ATLAS continues its cosmic journey through our solar system, carrying secrets from distant stars that may forever change our understanding of the universe. Whether it's a natural wanderer or something more extraordinary remains to be determined. What do you think this mysterious visitor really represents? Share your thoughts in the comments below. If you enjoyed exploring this cosmic mystery, like and subscribe to Sci and Y for more incredible space discoveries. Until next time, keep looking up and questioning the universe around us.